Today I'm going to give you a little introduction to equilibrium and what it is and talk about the equilibrium constant. So thus far in this class we've really only talked about reactions that go in one direction, just in the forward direction. But if you remember back to honors, we did talk a little bit about equilibria and reactions that can go both ways. So a reversible reaction is one in which can proceed in both the forward direction and the reverse direction, which is what it sounds like. And dynamic equilibrium, which again is also review, is a condition in which the rate of the forward reaction equals the rate of the reverse reaction. So if we look at this graph here that I've shown, the rate of the concentration of the products is increasing as the time goes forward, and the concentration of our reactants is decreasing as time moves forward. And at a certain point in time, if we wait long enough, those concentrations appear to stop changing. So it looks like the reaction is done. But really what is happening at this point is dynamic equilibrium. So since the forward rate equals the reverse rate, the concentrations don't change, but the reaction is still happening. It's just that each time you form a reactant, or reform a reactant, you also form a product. And so overall, it doesn't look like anything is changing. Now, to express this this process, this equilibrium condition that I just talked about, we use something called the equilibrium constant, which is just a way to quantify the concentrations of reactants and products at equilibrium. And the law of mass action is a law that relates the balanced equation to the expression for the equilibrium constant. And so what that looks like is, if we have a reaction AA, where little a is the coefficient, plus BB goes to CC plus DD, and this is a reversible reaction, then we can write our equilibrium constant, which is K. Now this is a capital K, different from the rate constant little k. And that will be the concentration of C to the C times the concentration of D to the D over the concentration of A to the A times the concentration of B to the B, all right? And so what you can see here is that your equilibrium constant K, the products are on the top and the reactants are on the bottom. And so the value of the equilibrium constant can tell us something about which side of the reaction is favored, or which direction the reaction goes more, whether the forward reaction or the reverse reaction is favored. So if the equilibrium constant is much, much bigger than 1, then that favors products because it favors the forward reaction. So it means the forward reaction goes almost to completion and the reverse reaction doesn't really happen much at all. This is basically all of the reactions we've done so far. This is what we've assumed. All right, so if Kc is much, much less than 1, then this would be a case where the reverse reaction is very favored. And so you're going to end up with almost all reactants when your reaction reaches equilibrium. And then the final example is where Kc is approximately 1. And in this case, neither the forward nor the reverse is favored more than the other. And so you end up with pretty close to equal amounts of reactants and products when the reaction reaches equilibrium. All right, so now let's write a couple of equilibrium expressions. So for our first reaction here, we want to write K is equal to, and we put our products on top, so it'll be the concentration of H2 squared, because there's a coefficient of 2 next to H2, times the concentration of O2, and that'll be divided by the concentration of H2O squared, because again, it has a coefficient of 2. And for the second one, our equilibrium constant would be the concentration of CO2 times the concentration of H2 to the 4th power, divided by the concentration of CH4 times the concentration of H2O squared. All right, now for those of you who are mathematically inclined, this should make perfect sense. For the rest of you, it might take a little getting used to, but we can easily manipulate the equilibrium constant for different reactions if they're related to each other. So let me go through the examples, and hopefully it will make some sense. So if we have the reaction I just told you where AA plus BB goes to CC plus DD, and the equilibrium constant that we just did on the previous slide, if you reverse the chemical equation, you invert the equilibrium constant. So what we've done here now, we have C and D as reactants and A and B as products. And so if we were to write out the equilibrium constant, we'd have A and B on the top and C and D on the bottom. And this is just equal to 1 over K. That was our original equilibrium constant. So we don't even have to write all of that out. We just know that if it's the reverse reaction, we just do 1 over the equilibrium constant for the reaction we started with. All right, the second is that if you multiply the coefficients in the equation by a factor, you raise the equilibrium constant to the same factor. So here, if we multiply all the coefficients by 2, so the coefficient for reactant A would be 2A, for reactant B would be 2B, and so on, then the result of that is now each of those coefficients has to appear in the exponent up here. And what that is just the original equilibrium constant that we had squared. All right, so if we multiply the whole thing by 3, we would cube the equilibrium constant. If we multiply it by 4, we would take it to the 4th power, and so on. Right. The final one is if you add 2 or more individual chemical equations to obtain an overall equation, you multiply the corresponding equilibrium constants by each other to obtain the overall equilibrium constant. So here, if we have A plus B goes to C plus D, like we've been using, and now let's say we have another reaction that we're interested in, and that's C goes to E plus F, with the coefficients little c, little e, and little f, then the equilibrium constant for that new reaction is e to the e times f to the f over c to the c, right? Now, if we add these two reactions together, then the c's cancel out because we don't, we have one on each side, so they cancel each other out. So our overall reaction now is A plus B goes to D plus E plus F. Okay, so if we know that, we could write out the overall reaction rate that we have here, which is there on our screen. You can also get that by doing this K times this K, which is what's shown here. And what you see is that these C's cancel out, and that gives you the new equilibrium constant that we just found down here. So the K overall in this case is equal to K times K prime. And the reason why this is so useful is because usually our equilibrium constants are given to us as numbers, not as expressions relative to the reactants and products. So in this case, we have a reaction at 25 degrees. It's N2 plus 3H2 goes to 2NH3. And the equilibrium constant for this reaction is 3.7 times 10 to the 8th. So this is a really, really, really big equilibrium constant, which means that it's going to favor the forward reaction, and we're going to have lots of products. So the question is to calculate the equilibrium constant for the following reaction at the same temperature. And it's important to note that equilibrium constants are temperature dependent, so you need to be at the same temperature to use these relationships. And so in this case, we have 24NH3. So now NH3 is our reactant, whereas it was a product above, plus, or goes to 12N2 plus 36H2. Okay, so what we've done is our K for our new reaction, I'll call it, is equal to 1 over the K for our reaction above, so 1 over 3.7 times 10 to the 8th, because we flip the reaction the other way, and we've multiplied all of the coefficients in this equation by 12, which means we'll take the reaction to the 12th power. So this is an incredibly, incredibly small equilibrium constant. You could calculate it out. My calculator actually will not calculate a number that small, but your newer, fancier calculators might. But the equilibrium constant would just be 1 over 3.7 times 10 to the 8th, the entire quantity to the 12th power. Right, now we want to predict the equilibrium constant for this new reaction given the equilibrium constants for the first and second reactions given here. So the first reaction here is CO plus H2O goes to CO2 plus H2, and the second is CO plus 2H2 goes to CH3OH. Okay, so the first reaction we're actually going to have to flip the other way because we want CO2 to be a reactant. So we can do that, and the coefficients stay the same. So we know our new equilibrium constant is going to have to equal 1 over K1, and then for the second reaction, that one is going to stay just like it is, and we're going to just add the two reactions together. So our COs are going to cancel out, and we'll add the H2 from the top reaction to the two H2s in the bottom one to get three H2s in the final reaction. So our equilibrium constant for this reaction is going to equal 1 over K1 times K2, which is just K2 over K1. And you could plug those numbers into your calculator and figure out what they were going to be, but that's the gist of it. And then the last thing that we're going to do is I just wanted to show you that the equilibrium constant can also be expressed in terms of pressure. So gases obviously have a particular molar concentration, moles per liter, but they also can be expressed in terms of their pressure in atmospheres or in millimeters of mercury. And so what I've been dealing with so far is the Kc, which is the concentration equilibrium constant, but you could also express it in terms of pressure, which we call Kp. So I'm not going to spend a lot of time doing that, but if you needed to get from one to the other, you could convert your concentrations using the ideal gas law. So that concludes our discussion of an introduction to the equilibrium constant, and we will build on this more in the next lesson.